Hello, I am Marie Platenius-Mohr. I'm with ABB Corporate Research, working as a research scientist in our software architecture team. And I would like to present to you our work on software architectures for edge analytics, which is joint work with my colleagues Hadil Abukwaik, Schlake, and Vach.
We all know the IoT comes with an increasing number of smart devices. This is especially true in the industrial sector, like in process automation. For example, here we see a wastewater plant. An industrial plant like this often comes with 100,000 of devices, like different kinds of sensors, for example, all sending data that wants to be processed. In the last decade, there was a trend towards letting the cloud manage all this with its powerful big data processing. Now, more and more companies also go for edge computing, complementing the cloud. Computing nodes are placed close to the devices so that you can do the data processing where the data is actually generated and where its results are to be consumed. This means that only filtered and/or aggregated information must be transmitted to the cloud, which means that more and more data can be considered in less time, which will improve and speed up the decision making and thereby also increase efficiency and productivity. Speaking of trends in industry, we all also know this. There are more and more analytics and AI and ML applications in industry, and we can expect this to increase even more in the next years. And these analytics applications can benefit a lot from the edge computing advantages, as they often need to process huge amounts of data. Especially the edge's benefit regarding low latency, meaning the ability to process real-time data, is essential. Since lag time is minimal, real-time data can be considered and insights can be delivered faster. And that's why the area of edge analytics evolved. Analytics applications that are deployed on the edge. Use cases for edge analytics can be found in various business domains, not only in process automation, but for example also in smart cities and smart transportation, public safety, and so on. How to design an edge analytics system is a topic for several research areas, but especially from a software architecture point of view, it raises many questions. For example, which layers and components should be part of an edge analytics system? How should they interact? How should they be connected? Which functionality is deployed where? Which should be on the edge? Which should be on the cloud? Which other factors influence the architectural decisions for edge analytics systems? And looking at related work, there are already many overview papers and surveys for this intersection in software architecture and analytics, AI and ML systems. This is an increasing trend, also in software architecture, of course. And there are also many surveys about edge computing papers. And we know there are a lot of edge analytics papers. However, a good overview or survey of those is missing. So the contribution of our paper is to give an overview of the edge analytics topics from the perspective of our own experience from industrial projects. And we also review existing approaches for edge analytics and compare them from a software architecture point of view. This topic is relevant not only for academia, but also for industry and also for various domains and use cases. We looked into many publications, but for this paper we selected 10 approaches for a more detailed investigation. We selected those publications that specifically address the software architecture, while we excluded approaches that mainly address other aspects of edge analytics, for example, the algorithms. The selected approaches address different domains and use cases, for example, smart cities, smart transportation systems, healthcare, but some are also for general IoT applications. Most of the selected approaches process time series of telemetry data collected from sensors, but some mention also other data types, for example, video processing, which is actually a big topic in edge computing. Most edge analytics approaches process real-time data, meaning online data streams, except for one approach serving badges in our selection. As already illustrated earlier, the typical edge analytics architecture consists of 3 layers, and this has also been confirmed by our survey. The devices layer includes the field sensors and controllers. The edge layer includes edge nodes that serve as a gateway to the cloud and it also hosts analytics-related components. The understanding of this edge layer is very diverse and ranges from one or few relatively powerful compute nodes to rather tiny, very resource-limited devices, but there may be a network or a mesh of them as well. The cloud layer usually includes analytics model management and dashboards for visualizing the results. The data flows from the devices layer to the edge and, most often in filtered or aggregated form, from the edge to the cloud. Depending on the use case, the results of data processing are returned back to the devices or are only accessed in the cloud, for example, using a dashboard. Depending on the use case, the devices producing the data and those consuming the results, which can but are not necessarily the same, could be either stationary or mobile. The device's data may also be collected and pre-processed by an intermediate system, like a control system, before it is sent to the edge. The data that is collected and processed can be manifold, structured or unstructured data, and any kind of data types like time series, telemetry, events, audio, video. Usually, the produced data by the devices is received at the edge as streams of real-time data, although there are also use cases and solutions for batch processing. As common in many IoT systems, communication is usually message-based via the MQTT protocol. There are multiple technologies for that. The components are often deployed as Docker containers. Of course, there are many more concrete instances and variants of such an architecture, which I have just shown. This diagram provides an overview of the features and their variants that we collected while reviewing the selected publications. It is not supposed to be a complete collection, but it gives a first idea of the design space and of the variety of solutions that have been published. The first level of the feature diagram separates 4 subtrees: the data processed at the edge or by the edge analytic solutions, the edge layer, the cloud layer, and the quality properties considered in the selected publications. The data subtree is further characterized by the different kinds of input providers and output consumers, the types of the data being processed, and the data mode. The edge subtree informs about the different roles at the edge, the multiplicity, and the functionalities and components hosted at the edge. The cloud subtree focuses on the different functionalities and components hosted on the cloud. In addition, we looked into different kinds of quality properties like network-related quality properties or also data-related quality properties. For time reasons, I cannot go into detail for each of these subtrees now. However, all the details can of course be looked up in the paper. We also detected many open research challenges when it comes to edge analytics. For example, one question is how to deal with a network of edges. In a distributed analytics setting, you gain advantages like improved robustness and scalability, but it may also produce communication overhead. It needs to be investigated which setting is optimal in which situation. Furthermore, in the real world, we usually do not have perfect data. We have incomplete, noisy, and imprecise data instead. There are approaches for adding additional components for incomplete dataset recovery on the edge, which seem promising, but need more evaluation taking into account the complete and the concrete architecture. There may also be cases where we want to intentionally produce a decrease of data quality for the sake of better efficiency in terms of bandwidth reduction or general performance. How to best deal with this trade-off depends on the specific edge properties and again on the architecture. Another open challenge is the topic of retraining. There are approaches where the training of the ML model happens in the cloud while the trained model is then deployed on the edge, but to enable a smooth retraining workflow when it comes to model degradation, there are research topics like AI ops and ML ops come into play.
To summarize and to conclude, edge analytics gains more and more interest both in academia and in industry, and also for many different domains, and we have seen many different use cases. There are a lot of approaches already there. However, there are also still a lot of open challenges, especially from a software architecture point of view. And there are many aspects to consider when designing an edge analytic system, as we have seen in the feature diagram. And this addresses all layers, the devices layer, the edge layer, and the cloud layer. And it concerns various quality properties. Thank you for your attention, and I'd be happy to answer your questions. Please don't hesitate to contact me.